So as you guys know, ants are these incredible creatures that are able to pull many times their own weight. In fact, if there was an ant that was anywhere near as large as we were and we were having a battle with that ant, we would just lose terribly. Let's hope we never get into a situation where ants take over the world. So they're notorious for being able to carry many times their own weight, right? If a 0.0001 kilogram ant applies a 0.00034 Newton force to drag a 0.0001 kilogram moth carcass at an angle of 15 degrees from the horizontal surface, how much work does it do? Okay, so we're going to use this situation to kind of practice these work problems that we've been talking about. Okay, so in this case, I have a moth being dragged this way, okay, and it's applying a force this way. Okay, so this is the force of the ant, and this is the displacement here. Okay, and I'm saying, so if this is the moth, whoosh, I don't know if that looks like a moth or not. I don't think so. I don't know, it's terrible. Okay, that looks more like a butterfly, but all right, let's just say it's a butterfly, whatever. If it's a butterfly, it has to be prettier. Okay, everything still applies. Okay, and so this ant applies a 0.00034 Newton force. Okay, and this moth over here is 0.0001 kilograms. Right, that's the mass of this guy. Okay, so the question is, if the ant takes this moth 15 centimeters back to her colony, how much work does the ant do? So this D here is 15 centimeters or 0.15 meters. Okay, well, as we know, work is just equal to force dot distance, the force vector dot the displacement vector, right? And that is equal to F d cosine theta. True story? True story. In this case, the magnitude of the force that the ant applies is 0.00034 newtons. The displacement, as it says, is 0.15 meters, right? And the angle between them, the problem says, is a 15-degree angle. Okay. What is the work that it does? Well, according to me, what I have here is 4.9 times 10 to the minus 5 joules. Let me know if that's wrong. Okay? All right. Part B, though, says if there's a coefficient of kinetic friction between the moth and the ground of 0.32, how much work does friction do on the moth? Okay, so if this moth is being slid across the ground in this direction back to the little colony over here, right? Let's say this is the colony, right? There is going to be a frictional force resisting it in this direction, right? And it's going to be kinetic friction. True story, right? Okay, so this is part A. Part B, which I'll write over here. Part B says, what is the work done by friction? One thing to know is that every force that's being applied to this guy is going to do some amount of work on him, right? So we need to be careful and make sure that we're accounting for all the forces, okay? In the next slide, we're going to be talking about network, which is summing up all the work done by all the different forces acting on an object. So how would we find the work done by friction? Well, again, this is our formula. Work due to friction is going to be equal to the force of friction times the displacement times cosine theta, right? But we need to find out what that frictional force is, right? Remember, frictional force is the frictional coefficient times the normal force. And in this case, the butterfly is just laying here on the ground, right? And so the normal force is in this direction, and the weight mg is in this direction. So N must equal to mg if there's no net force in the y direction, right? So I can just replace this with mu k times mg, right? So in other words, if mu k, as the problem says, is 0.32, right? And the mass of the butterfly is 0.0001, as I say over here, right? And gravity is 9.8. Then I have a kinetic friction, right? Friction is resisting this motion at a force of 0.003 newtons. I think, is that right? Is that correct? Yep, looks good to me. Looks good to me. 0.0003 newtons. Okay. All right. So how do I find the work done by that frictional force? Well, I just take that and I put it in there. So the work due to friction is going to be 0.0003 times the distance, which is this frictional force is resisting the moth's motion for that entire 15 centimeters, right? So that's going to be 0.15 again. But here, the cosine of the angle is what? D is this way, and the frictional force is this way. So that's a full 180 degrees. And that has the effect of just making this negative. Remember I said in the last slide that if a force is moving opposite the direction of the displacement, it has a negative work, and that is definitely true in this case. I'm getting a negative work of negative 4.5 times 10 to the minus 5 joules. Okay. Okay. So the actual ant does work of 4.9 times 10 to the minus 5 joules. Positive work because the force is in roughly the same direction as the displacement, right? This is less than 90 degrees. But the frictional force does negative work. That's negative 4.5 times 10 to the minus 5 joules because it's in the opposite direction, okay? Now, if you go to the next slide, this is net work. If there is more than one force acting on an object, each force does a certain amount of work. Just like it is important to calculate net force, it is also valuable to calculate net work acting on an object. Okay, and this will become more clear why net work is important when we do the work energy theorem, which we're going to discuss next. But for now, what is the net work in this case, right? Where due to both the moth and the friction, due to the ant and the friction. Okay, well, the net work, we'll call this C, right? Work net is just the work of the ant plus the work of the friction. Okay? The work of the ant plus the work of the friction. You're just adding up all the works on all the forces that are acting on the moth, right? But there's only two forces, the ant and the friction, and the work of the friction is 4.9 times 10 to the minus 5, right? And the work of the ant is 4.9 times 10 to the minus 5. The work of friction is negative 4.5 times 10 to the minus 5, right? So you just take that plus that, right? Adding a negative, basically you're just subtracting this 4.5 times 10 to the minus 5 divided by the 4.9 times 10 to the minus 5, right? And you get a net work of 0.4 times 10 to the minus 5.